Hello all. In this session, we discuss local Sech algorithms. In my last session, I told you about importance of a Seching. So in AI, in a artificial intelligence environment, Sech is a fundamental way of solving any problem. That means any AI problem, if we want to solve, first that problem is formulated as a Sech problem. Then we apply one Sech algorithm on that Sech problem. We find the solution to that problem by Seching several options. Let me give you a small example about how we drawn a water jug problem in last session. Suppose I have two jars. Suppose I have two jars. One jar can hold 4 liters, another jar can hold 3 liters. And there are no markings or measurements on these jars. Here my problem is I want to, without any markings or without taking any other third party help, just with the water pouring on the ground, I have to fill the first jar with 2 liters. And second jar can be anything like 0 or any other. So this is my start state and this is my goal state. So when I try to solve this water jug problem, what I do, first I formulate into a Sech algorithm, means formulate into a Sech problem where I try to draw one state space diagram of this problem. State space diagram nothing but what is the starting stage of my problem? Initially, both jars are empty, 0, 0. Then I try to draw state. Now, what could be the next state of this problem? Now, somebody may fill the first jar with 4 liters, and another one may fill second jar with 3 liters. These are the two states from the first state 0, 0. From 4, 0, I can go into the states like I can go into a new state of either 0, 4 or I can go into another state of 4, 3. So in 4, 3 again, from 4, 3 I can go into 0, 3 state or 4, 0 state. So from 3, 0 I can go into a 3, 3 state or 3, 0 state. From 3, 3 I can go to 4, 2 state or some other 3, 0 state. From 4, 2 state I can go to 0, 2. From 0, 2 I can go to 2, 0. Means here my starting state is 0, 0 and my goal state is 2, 0. To achieve from starting state 0, 0 to 2, 0, I have constructed one state space Sech where each state represents what are the next possible state from this state. So after drawing our entire state space Sech, now apply a Sech algorithm. How can I reach my goal state starting my starting state? Which path I should follow to reach my goal state. Like this, every AI problem is basically converted into some Sech problem, and we apply a Seching algorithm on that problem to find the path between a goal and a final state. Now, this is any like I have given example of a tic-tac-toe. There also I converted into a state space Sech and I Seched the solution. Now, this is a normal state space Sech. So, these are the, as I told you, first step in solving a problem is we have to convert that problem into a Sech problem and then apply search algorithm. Now what is a search algorithm now? First type of search algorithm is a linear search algorithms. Linear search algorithms are a class of optimization algorithms used in AI to find solutions for optimized problems. So what is the optimized problem and what is a linear search problem? See, as we know, we draw a state space search of a problem. We try to find the paths. Suppose we take one n-queen problem. This is one n-queen problem where 4 queens are placed on a chessboard of 4 by 4 board, and now I design one constraints on this board that my final, if somebody wants to play this game and win the game, he should reach a state where no 2 queens are in the same line, in a vertical line or in a horizontal line or in a diagonal lines. If they successfully place these 4 queens in their corresponding position such that it satisfy all the constraint, basic constraint is that no 2 queens should oppose each other. They should not place in a vertical line, horizontal or diagonal. So to solve this problem, I created one state space search. Now this is a starting state and these are my goal states. Leaves contain goal states. Now in general state space search, we search for a path in other algorithms like BFS, DFS, breadth first search, depth first search, where I find a searching algorithm from goal to from starting node to the goal node, and I find the path. But here local search algorithms they are not for finding the path. They are basically, they try to treat every state itself as a goal, so that they don't explore entire state space search. They do only a specific set of, they form a random solution and they try to iteratively improve that random solution and try to find the goal state. So rather than searching a path, they focus on the finding the correct state of the game to win the game. Now that is what basic local search algorithms work. So basically local search algorithm is nothing but a algorithm that uses one random approach. It gives a random solution and it applies this random solution on the problem, and if it is not reaching the goal, makes a slight changes to that algorithm and again reapply that algorithm. Suppose now one live example, suppose we meet a doctor like a ENT doctor. Suppose you want to take the glasses. How a doctor prescribes the lenses? First he takes randomly, he gives one lenses based on your symptoms and he asks you whether those are visible or not. Based on your input, again he changes the new lenses. He tries to improve his solution until he gets you the correct lens for your eyes. That is nothing but is indirectly applying a local search algorithm. He is not exploring entire state space of your problem, only giving one random solution and improving that random solution step by step so that it gives the correct measures. So such kind of algorithms we call them as a local search algorithms. So local search are particularly useful when solving large and complex problems. See, when we try to solve a large complex problem, generally we get a very big state space search. So when a very large state space search, exploring entire state space search, it becomes very problematic. So what we do, we only explore some part of the state space search. If we find our goal state, there itself we stop the algorithm. Now this is a basic idea behind a local search algorithms. So first we write a random state, we write the code, we prepare one random state. Like in my n-queen problem, so I take these are the, I can explore from starting to, there are possibilities of 12 possibilities from the starting state. So what I do are I apply one heuristic to every state. Heuristic function, I apply heuristic function like estimated function. How much cost I need to reach this state, how much cost I need to this state, how much cost. Based on the cost estimation value, it tries to find whichever the best one. We call it as an objective function. That objective function decides quality of the state. Suppose from this state, this may go into this state, this state, this state. 4 possibilities are there. Now it calculates one a cost function. Whoever cost estimation cost is less, it tries to choose that state. So this is like first we have to prepare one random state. We take one random state and we set that random state as a current state. Then we check whether is it a goal state or not. If it is not a goal state, we run a loop. So we run until we try the best found. We iterate this loop. So if all the possible states are over, then we return. If otherwise, every time I prepare a neighbor. See here, these 4 are neighbor. Who is the best neighbor? Suppose this is the best neighbor. Then again I explore who is the next best neighbor out of these 4. This is the best neighbor. Then like this, every time I generate the neighbors, and I try to whether the neighbor is can be a current state. If the cost of reaching that neighbor is less, I make him as a current state, and then I explore remaining solutions from that neighbor. Suppose cost of here out of these 4, cost of reaching this state is suppose it is less. It makes it as a current state. From this current state, then again checks that which is the cost of which state is very less. Objective function calculates that state and goes to that state. Like this, rather than exploring entire search, it only explores best found approaches and gets the best found. Means your searching time decreases a lot because you are not finding the path. That is why here we have to talk about 2 things in this local search algorithm. One is satisfaction versus optimization. Satisfaction means your goal satisfaction. Here my goal is to find the state where no 2 queens are in the same lane or diagonal or in a burn. If I reach that state, no matter whichever path I followed from starting state to the ending state, if I reach that state, we call it as a satisfaction problem. So if by applying my constraint, what is the constraint? My rules of that game are constraints. By satisfying those constraints, if I reach the goal, that is a satisfaction problem. But optimization problem is not about satisfaction, finding the best route. So anyway, finding the goal is not important. Finding the optimized way where my cost is very less. So when I apply a optimized way of finding the state, that is called as optimization. So these 2 means our local search algorithms are basically used for solving a optimization problems. Optimization problem indirectly uses heuristic function of a local search algorithms to explore only few section of my state space search. So these are some local search algorithms that we are going to discuss in next few sessions. First hill climbing algorithm, simulated annealing algorithm, genetic algorithms, taboo search, anti-colony optimization, local beam search, iterated local search, and variable neighborhood search. These are different local search algorithms. Basically these algorithms, they just every algorithms only do one thing. It randomly choose one solution, tries to improve that solution iteratively through different heuristics, and try to find the best solution for our problems. So we discuss one by one in next few sessions, and these algorithms solve my optimization problems. Optimization means trying to finding the best solution to my problem. So again we discuss these problems by applying those algorithms like traveling salesman problem, knapsack problem, job scheduling, n-queens, constraints, machine learning model, graph coloring, and network design. So in next few sessions of this second unit, we learn these algorithms one by one and apply these algorithms for solving these optimization problems. That is what. Thank you.